Welcome, my friends. In this video, I'll be discussing section 5.3, the confidence interval for the population mean. Here is the formula that we will be using for the confidence interval to estimate the population mean. X bar is the sample mean, t is something called the t-score from the t-distribution, which we will talk about shortly, s is the sample standard deviation, and n is the sample size. We call the sample mean, x bar, the point estimate for the population mean. It's our best estimate of the value of the population mean. T times s over the square root of n is what we call the margin of error, sometimes just called the error. The margin of error is made up of two components. First, we have the t-score, which we call the confidence level multiplier, and then we have s over the square root of n, which is the estimate of the standard error of the sample mean, or in other words, on average, how far you would expect the sample mean to differ from the population mean. The easiest way to visualize the confidence interval is with a number line. The sample mean of x bar will go right down the middle, and then we'll have our lower and upper bounds somewhere to the left and to the right of our point estimate of x bar. The distance between x bar and either the lower and upper bound is the margin of error, which is t times s over the square root of n. Okay. Before we can look at a full example, we need to discuss the t-distribution and the t-score. So recall that the z-distribution is a normal distribution that has a mean of 0 and a standard deviation of 1, and looks something like this. The z-distribution utilizes the population standard deviation. In this section, we will use the t-distribution, which also has a mean of 0 and a standard deviation of 1. But instead of utilizing the population standard deviation, we will utilize the sample standard deviation. So the t-distribution will look very similar to the z-distribution. We'll just be using s rather than sigma. Since our confidence intervals are always going to be built based on information from a sample, it makes a lot more sense to use the sample standard deviation, meaning we will not be able to utilize the z-distribution, and instead we will be using the t-distribution. Now note that the t-distribution is actually what we call a family of distributions, and it's going to look a little bit different depending on the sample size. Technically, we call this the degrees of freedom, and the degrees of freedom can be found by the sample size minus 1. So depending on the sample size minus 1, or the degrees of freedom, the shape will change ever so slightly for the t-distribution. Now it turns out the higher the sample size or degrees of freedom, the more similar the z and t distributions will be. So with smaller sample sizes, the t and z distributions will be more different, but with a larger sample size, they will be very similar. Here's what the z and t distributions look like for a sample size of 6, which means the degrees of freedom are 5. The z distribution is in black, and the t distribution is in green. Sometimes it's said that the t-distribution has slightly thicker tails than the z-distribution, meaning more extreme values are slightly more likely. So how do we find the t-value or the t-score in the confidence interval formula? Well, similar to how we found the z-score in the confidence interval formula for the population proportion, we're going to be using an inverse function. But instead of inverse norm, we're going to be using what is called inverse t, which works very similar to inverse norm. The inputs into inverse t are going to be what we call the area to the left, as well as the degrees of freedom, which can be found under second vars on the TI-84 calculator. Let's take a look at an example. Let's say the sample size is 21, which means the degrees of freedom are going to be equal to 20. I should maybe mention at this point that the technical meaning of the degrees of freedom is really beyond the scope of an introductory statistics class, so for us we will just think of it as the sample size minus 1. Okay, so if we have, let's say, a 95% confidence interval, then what you would like to do is put that 95% in the middle of the t-distribution, which, just like the z-distribution, is going to be symmetric and normal shaped. And then you're going to want to find out what area is in each of the tails of the distribution. So if we have 95% in the middle, then that means we have 5% left over to reach 100%. 5% divided by 2 is 2.5% in each tail. Now the t-score that we want is the t-score on the right-hand boundary of the shaded area. So if we want to find the area to the left, that's actually two different areas. It's the 95% and the 2.5%. 95 plus 2.5 is equal to 97.5%. To find the t-score, we would use inverse t with 0.975 representing 97.5%, as well as the degrees of freedom of 20. Let me show you this on the TI-84 calculator. So on the calculator, I can press second and then distribution or vars. And then I should be able to scroll down to option 4, which is inverse t. When it asks for area, it's asking for the area to the left, which is 0.975. And our degrees of freedom is 1 smaller than the sample size that was taken, so we're going to be using 20. And then we will get approximately 2.086. And that's the number that you would use as the t-score in the confidence interval formula. Note that if you have a TI-83 calculator, then it actually doesn't have the inverse t function. And you can install this function or program it in by following this video right here. So if you go to this video or just do a YouTube search for programming inverse t into a TI-83 calculator, you will be able to do that. Okay, so give this one a try. So let's say that your sample size is 30. See if you can find the t-score for an 85% confidence interval, a 90% confidence interval, and a 99% confidence interval. So go ahead and put that percentage in the middle, figure out what the area is in each of the two tails, take the middle area and add the left tail area, and then use that in inverse t with the degrees of freedom to find the t-score. Now you should notice, if you were to do this, that the t-score is going to get larger as the confidence level increases. And remember that the t-score is part of the margin of error formula. And as we said in previous videos, the margin of error is actually going to increase when we increase our confidence level percentage. And this is the reason why with the formula. If you increase the confidence level, then you're going to be increasing the t-score, and therefore the margin of error is going to increase. So go ahead and pause the video if you haven't done that already and complete these before we move on to a full example. Okay, so to do a full example, we're going to, just like we did with the population proportion, use the Fred technique. So as you might remember, Fred is John Gabrosik's dog, the author of the textbook. So here he is reminding us again to use the Fred technique. And Fred, each letter in Fred represents a different step that we're going to be using for our confidence intervals. So first we must formulate the problem. Then we must review the conditions that are necessary to do the confidence interval. Then we must execute calculations, and then finally draw conclusions. So what does that mean for a confidence interval for the mean? Well, if we are formulating the problem, that means we need to describe the population, we need to describe the sample, describe the quantitative variable that we've collected, because when we calculate the mean, that's from quantitative data. And then we should describe the population parameter that we're trying to estimate, which will be some sort of population mean. As far as reviewing conditions, I've mentioned this before, but one condition that's not specifically checked for in this textbook that you should always verify is there is a random sample. We should have an equal chance to choose anyone in the population for any stage of the sampling process. So make sure you have that. But additionally, the data should be roughly symmetric or only slightly skewed. And also the data should have relatively few outliers relative to the sample size. And typically the easiest way to check these two conditions would be to create a box plot or perhaps a histogram. Now at this point, I should probably mention that if you're using a different textbook or you Google the conditions in order to do a confidence interval for the mean, you're probably not going to see these two conditions. You're probably going to see that you need to meet one of two possible requirements. You're probably going to see you need to either have a large sample size, usually they say at least 30, or you should be drawing from a variable that already is normally distributed. And as long as you met one of those two things, then you'd be okay to move ahead with the confidence interval for the mean. But these are the two conditions that we're going to be using in this textbook. We should either have roughly symmetric or only slightly skewed distribution, and then also it's not an or, it's an and the data should have relatively few outliers relative to the sample size. Okay, the third step, which is the largest step, is to execute the calculations. And that's where we're going to be using this formula. We'll have to find the t-score using inverse t. We might have to calculate some of these other values from maybe like a 1var stats on the TI-84 calculator, and then finally plug into the formula. And the very last step is to draw conclusions, which will be basically by filling in this statement here. We are C% confident that the interval between our lower bound and upper bound contains, and then we will describe our population mean. So let's go ahead and look at an example. And this example is from page 235 of the Grand Valley textbook. It says the reaction time in milliseconds in a silent environment is given for 24 Grand Valley State University students. So I'm not sure exactly how they recorded the reaction time. Maybe like, I've seen them like maybe you drop like a yardstick and they're trying to, stop it as soon as they can. But somehow we have timed how long it takes for 24 Grand Valley students to react to something, right? And we are asked to find a 95% confidence interval for the mean reaction time of a Grand Valley student. So the very first step is to formulate the problem. And the first part of that is to describe the population. And it looks like we're grabbing information from Grand Valley students, so our population would be all Grand Valley State University students. Then we can go ahead and describe the sample, and the sample is going to be the 24 students that we have here. Then we can describe the variable. The variable that we have here is the reaction time in milliseconds in a silent environment. Finally, we can describe the parameter, which is the mean reaction time, not just of the values from the sample, but of all Grand Valley State University students in a silent environment, and that's represented by mu. Okay, the next thing we can do is we can review conditions. And to review conditions, we're going to want to create a box plot and possibly a histogram. Now, you may remember that the TI-84 calculator has the capability to make both of those graphical displays. So if you forgot, I will show you how to do that here. We can go into our stat list and then press enter to enter the stat list. And then we can go ahead and clear out the first list by hovering over list 1, pressing the clear key and then the down arrow. And then we can go ahead and enter in all of these numbers into the first list. So I'm going to do that right now. Okay, and I highly encourage that you also pause the video if you've got your TI-84 calculator and enter these numbers yourself. So now that I have all these numbers, I can press the second key and then the y equals, which I'm really getting into stat plot here. And then I can enter stat plot 1, press enter. And I'm going to want to make sure it says on next to stat plot 1, which it does. I'm actually going to also turn off my other plots. I think these might be on right now. So I can go in here and I'm going to turn off the other two so that it doesn't display some information I don't want, but they may not be on for you. So I'm going to turn that one off as well. You can also, if you go to y equals, you can easily see which ones are on. I can see plot 1 is on. So I'm going to go second, y equals again, go into plot 1. I'm going to go down and make sure I have the right graphical display listed here, which is the box plot. I want to use this box plot that shows the outliers and not the second one. So I'm going to press enter over that one. I'm going to make sure it says list 1. If it doesn't, you can say second and 1 for list 1. And then I shouldn't need to change anything else here. I can change the color if I want to, but it's not necessary. And then you can press the zoom key, or on some calculators, you have to get out of this screen first. So you might want to go second quit. And then maybe when you're on the home screen, you can press zoom, and then it's the 9th option for zoom stat. And then you'll get a good picture of the box plot, which we can see here. There's no outliers. We don't have any dots on either side, and it looks like it is roughly symmetric, right? When you have the median is right in the middle of the box, that's kind of representing a roughly symmetric distribution. So that's looking pretty good there. Let's change it to a histogram. So if I go back in here, I could change this to a histogram, which would be this one. And then I can go zoom 9 again. And I can see, looks like it might be a little bit skewed right, but it is still, it's not like extremely skewed or anything, right? So going back to our conditions, so here is a little bit nicer version of this. I think this is grabbed from the textbook, and this is kind of the vertical version. It said we have to make sure that the data is roughly symmetric. It does seem like it's roughly symmetric. There are no outliers at all in this case. I think it said there should be relatively few outliers relative to the sample size. So we've kind of met those two conditions, right? So therefore, we're ready to be able to move forward with the confidence interval. All right, then we can go to the execute calculation step, which means we have to use this formula here. And in order to do this, we have to find x bar, t, s, and n. And since we already have all those numbers into our calculator, we can use 1VAR_stats to get some of those numbers. So if I grab the calculator here, make this a little bit smaller here. And then if I go to the stat key again, if I've got all the numbers already in my stat list, I can arrow over to calculate and then choose the very first option for 1VAR_stats. Make sure the list says list 1, or I can press second 1 to get list 1. Go down to calculate, press enter, and I'm going to get all of the numbers that I need for in order to do this confidence interval. So we had a mean of 329.75. That's the number that we had here. Let me just mention now, I believe the textbook is incorrect here. I think they have a slightly different number for the mean, but I've typed these numbers in multiple times, and every time I'm getting 329.75. So this is what I'm going with in the video. Textbook could be fixed by the time that you're watching this, possibly. And then the standard deviation is 18.34. That's what we got right here. And then we have the sample size was 24, which is also given in the calculator. We can also find the degrees of freedom. We'll need that for the t-score here in just a moment, which is one smaller than the sample size, or 23. And we're doing a 95% confidence interval. So if we're doing a 95% confidence interval and we need the t-score, that's the one thing that we're missing at this point. You're going to draw the distribution with 0.95 in the middle. The t-score is the t-score kind of on the right-hand boundary, which leaves us with 2.5% or 0.025 in each tail. So the area to the left of the t-score is the middle area and the area in the far left, right? Those areas are both to the left, so we're going to use inverse t with those two numbers. So if I go and grab my calculator, second distribution, inverse t, and the area is 0.975, and the degrees of freedom is 23. And I'm going to get 2.07 approximately. So that's the t-score we're going to use in the formula. Okay, at this point, we are ready to plug into the formula. So we take x bar, which is 329.75, plus or minus 2.07, the t-score, multiplied by s, which is 18.34, over the square root of 24, the sample size. And if I grab my calculator, and I plug this in, I'll have 329.75. I'll do the minus first, 2.07, multiplied by 18.34, divided by the square root, second square root of 24. I get the lower bound, which is looking like 322.00 to 2 decimals. And if I press second and enter, I'll get that entire answer back again. I can scroll back and change that minus sign to a plus sign, and I'll get 337.50 rounded to 2 decimal places. So those are the two numbers I got there, 322.00 and 337.50. So that finishes our execute calculation step, and all we have left is to draw a conclusion. So remember, there is a template statement. Here it is. We are 95% confident that the interval between 322 and 337.5 milliseconds contains the population mean reaction time in a silent environment for all Grand Valley students. In other words, based on our sample, we were able to find a sample mean of 329.75 for the mean reaction time, but that was only based on a sample of 24 students. So we can't just rely on that number because there's a lot more than 24 students at Grand Valley. So based on this formula here, we're able to say with 95% confidence that the true mean, based on all the students at Grand Valley, falls somewhere between 322 and 337.5 milliseconds. All right, here is a problem for you to try. A random sample of 12 Grand Rapids Community College students who are enrolled in statistics this semester resulted in the following number of hours worked per week. The assumption is per week. And then we are asked to find a 99% confidence interval for the mean hours worked per week by GRCC statistics students. So you're given a small data set here, and here is the formula that we've been using. So go ahead and pause the video and see if you can complete all 4 steps of the Phred technique. So formulate the problem, and then review the conditions, see if you can make a box plot, maybe a histogram, and look at that. And then execute the calculations by using the formula, and finally draw conclusions by writing out a conclusion statement using that template. All right, that's all I had to talk about in this video, so I will see you in the next one.